Hello, and welcome back to our series on electricity and magnetism. We're starting part 2, and we're going to be in session 14 of our series. And all the basic concepts of part 1 apply to part 2. Now, if you didn't see part 1, you can still enjoy part 2, although I would recommend going through part 1 first if you have the time. In part 2, we will be exploring the practical electrical systems that power our homes, our offices, our commercial buildings, and our factories. In particular, we'll explore how we move electricity from one place to another, the electromagnetic devices that make that possible, the special kind of electricity that we need to use in order to make those devices work, and the kinds of generators that produce them. Now, in this session, we'll focus on the problems that real wires present. So, let's get started. We often interact with electricity very superficially. By that I mean, if we need to operate something, let's say I want to listen to this old-fashioned radio here. All I need is to plug this into the wall. I just look for an outlet, plug it in, and hope it will reach where I want to sit and listen to it. Now, if it's too far away, all I need to do is just grab the first extension cord that I get my hands on, you plug it in, and off you go. Similar situation with a power supply for a cell phone or a iPad, a notebook, a laptop. If it's too far away, just grab the nearest extension cord and off we go. Suppose I have to do some work in the corner of a room that's kind of dark and I don't want to use the little thing that I wear on my head or a flashlight. I need a lot of light to do a project, and so I might grab a light like this, and again, all I need is a place to plug it in. If it's too far away, I use the extension cord. If I were to draw a diagram of how all that's working, it would probably look like this. Here's my power source. Here's the thing that will make me happy. And I have my magic wires, because I didn't have to think about them. I knew they would do whatever I want them to do. Well, there is no such thing as magic wires, okay? The only reason I could approach this that way was those devices don't use a lot of electricity, and the capacity was there, and I didn't have to worry about what was going on in the wires. But there is something going on in the wires. It's called electrical friction. We call electrical friction resistance, okay? It's a resistance to the flow of electrons. Resistance is made up of really three variables. One is the length of the wire. The longer the wire, the greater the resistance. The cross-sectional area. The bigger the cross-sectional area is, the less the resistance. It's kind of like a water hose. The bigger the hose is, the slower the water can move, the less friction there is. The longer the hose, more friction, and so because of the high velocity, and I need more pressure. What's the third thing? The third thing is the inherent resistivity of the metal that the wire is made out of. Okay? Now, resistivity by its definition is a very tiny number. Well, what am I talking about? Well, when we define resistivity in the metric system, we're talking about a wire that's a square meter in area and only a meter long. By using that definition, we end up with resistances that are so tiny that if I were to make a table for you with this kind of a presentation, it would not be an intuitive kind of thing for you to say, oh yeah, that's better than that one. The numbers would be kind of strange. So what I've done is I've created a specific example, and then we will apply the different metals to that example. Our example is 1,000 feet of wire, and the size, the diameter, is based on a number 14 wire. Okay, well, we'll talk about gauges a little later in this session. But the number 14 wire, here's some copper wire of that gauge, rather thin. It's a little thinner than the lead of number 2 pencil. And in fact, we're going to actually do experiments with 1,000 feet of wire in 2 particular sessions. Here's 1,000 feet of number 14 wire. Now this is insulated, so it looks a little thicker. Now you see 500 written all over it. The reason is I've got 2 different conductors here. One up, one back. So it's 500 feet up, 500 feet back, or 1,000 feet. Okay, so 1,000 feet of number 14 wire, and it's 2.5 ohms of resistance. Now ohms are the unit of measure for resistance. Let's take a look at the different metals. If we were to make that coil of wire out of these different metals, silver would be the best. It's only 2.4 ohms, but copper is very close. And then there's aluminum, which is not bad. But then as we go to these other materials, they start to really, the resistance starts to get very large, and some are more expensive. They have certain characteristics that would not make them appropriate for extension cords or power lines. So mainly our power system is for moving electricity around in buildings or transmitting them long distances, or either copper or aluminum. And the way the way it's working out, mostly the copper is inside of buildings and the aluminum the outside, but I wouldn't say it's always that way. Okay, but that tends to be the direction we've been heading. We don't use silver, even though it's slightly better than copper. The copper for that roll I showed you would probably cost $60, just the copper. If we made that out of silver, it would cost $7,000, and that is why we don't use silver. Silver is very expensive. It's used in very special cases in either laboratories or perhaps in our digital circuitry if needed. But for what we're talking about, we're either going to be dealing with copper or aluminum, and I would say pretty much our experimenting is going to be with copper. Now this word equation can be simplified to this: resistance equals resistivity times the length of the wire divided by the cross-sectional area. Now, this is important whether we are running a couple of hundred feet of extension cord to the back end of the yard, or if you're a contractor on a job site and you've got all these different power tools you've got to operate. It matters how this resistance affects you. Or if you're wiring a house or an office, and especially if you're moving electricity a mile, 10 miles, 100 miles, maybe 1,000 miles. In fact, in order to make these systems work, our utility systems, we have to use some special devices. And just to give you a little bit of an intro to that, let's take a look at these two. They use the same principles that allow us allow us to travel, send electricity long distances. And we'll get into those in some future sessions. So let's take a look at how, now that we know about resistance, how that affects the circuit that we had way at the beginning. So here's our source again. Here's the device we want to operate that makes us happy. Except now, these are not magic wires anymore. Each leg of the circuit has resistance. The RW stands for resistance of the wire. And I have two of them here. I've got this leg and this leg. This is the symbol you use for resistance in electrical engineering. It represents the resistance from here to here, not just in the middle spot. It is the whole thing is what that represents, the whole distance. Now when we run amperage through that resistance, something happens. So because I have two of them, you'll notice here in this formula I have 2 RW. Okay, I could put RW plus RW, or I can put 2 RW. 2 RW times the amps equals the voltage that's lost. Okay? It's wasted. It's used up moving the electrons from the source to my device and back. Okay? So we already have a problem here. Voltage is being used up. Hopefully it's a very small amount, but we can't count on that. You also know that volts times amps equals power in watts. So if I'm losing this much voltage and I have that many amps flowing through the circuit, then the voltage lost times the amps equals the wattage that's lost. Where does that wattage go? It goes into heat. So you see, we have two issues with real wires that have resistance. They cause a loss of voltage. We call that voltage drop in the industry. And we're generating heat. Now, if we lose too much voltage, then even though we had enough voltage over here we may not have enough, and our device might not operate. Or worse yet, it could be damaged. Now we're going to deal with voltage drop in some future sessions. And in this session we'll finish off by talking about how do we deal with the problem of heat. Okay, conductors producing heat. So I've got a piece of wire here, this thin one here, and I start pushing amps through there. And if I push a lot through there, I'm going to produce a lot of heat, and pretty soon it can't dissipate enough heat. It's going to get so hot that it will melt the insulation. Or it might get to the point where it gets so hot that it can ignite combustible materials. Now, there's certain circumstances where it's okay for it to get hot, okay? Those are very limited examples. I showed you a wire here, one of the metals, nichrome, okay? 161 ohms in that 1,000 feet. So we don't have to have very many feet to get substantial resistance. We use those in heaters, like a space heater, or a toaster oven, or a toaster. It's okay for things to get hot when they're enclosed in an apparatus that will keep us safe. But we don't want that to happen in the walls of our house, or our office buildings, or our factories. So what do we do? Well, let's take a look at a panel, an electrical panel. So here is a panel at my house, and let's open the little door, and there we have a bunch of switches. That's the big switch there, and these are the little switches. We don't call them switches though, do we? I bet you know they have a different name. Yeah, they're not just switches. They're called circuit breakers. So this is a circuit breaker. Let's take a look at close-up of a circuit breaker. My circuit breakers have different colors for the different capacities. If you look at this one here, you'll see it's got 20s. The red ones have 20s on the end of the switch, and the blue ones have a 15. What that means is that that is the amperage at which the circuit breaker will turn itself off. So if the electricity flowing from the circuit breaker to your outlets or to a specific appliance exceed the numbers on the circuit breaker, they will turn it off. Let's take a look again at that panel. Let's look inside. And you'll see there's all different size. Whoops, let's get to the panel here. You'll see there's all different size wires in there. There's probably four, I think I've probably got 4 gauges of wire in there. Let's take a look at what typical gauges you might find in your home. Zoom out a little here. There we go. Now the thing about gauges, and I'm not going to explain why, the smaller the number, the thicker the wire. Okay? Now not the insulation doesn't matter, it just needs to be adequate. But these numbers correlate to the actual conductor and not to the size of the insulation. So notice that 6 is the thickest and 20 is the thinnest. Now the only wires you would use for power in a building are 14 or larger. Larger in size, smaller in gauge. These 2 real thin ones you might use for what's called limited power low voltage control circuits, like your thermostat for your heating and cooling system, and also perhaps a garage door opener, doorbell if you have one. They have a little transformer that produces a low voltage, limited power, and that's the only place you would use skinny wires like that in wiring your house. You need to stay in this range right here. Now, because of these different thicknesses, they have different amperage capacities. And so, like we were talking before, the wires that come off of here need to be able to handle the rating of the circuit breaker. This is a 20 amp circuit breaker. This wire needs to be able to handle 20 amps in the situations that you find them in a building. It's not out in open air, so it's often in a space where it doesn't dissipate heat rapidly. So they have a certain rating by code, and this is a number 12 wire that goes typically with a 20 amp circuit. Now you can make it can be thicker. There's no problem with it being thicker. A little harder to handle because it starts to get really stiff as it increases in diameter. But it can be thicker, it'll cost more, but it'll be safe. It mustn't be thinner. You don't want this to be a wire that gets hot at 15 when this isn't going to shut it off until 20. So, have you had a situation in your kitchen where someone's percolating coffee, somebody else is making toast, and you come in and want to make some, let's say, hot cocoa, and you pop in the milk or water into the microwave, push the button, and all 3 of them go off? Well, that's because you exceeded the capacity of your circuit breaker, didn't you? Heating appliances use a lot of power. They don't necessarily use a lot of energy throughout the year. You don't toast all day long. It's for a short time that you make toast. But while you're making it, you're probably drawing 7 or 8 amps. Coffee pots don't use a lot of power throughout the year, but when they're on, when they're percolating, they're probably using 7 to 8 amps. So we're already at 14 or 15. Now you throw in a microwave at 8, 9, or 10 amps, and we are way over 20. And if you had a 20 amp circuit breaker, even a 20, not a 15, but a 20, it's going to turn it off. A nuisance for you, but it protected your house from catching on fire. So these are the devices we use to deal with this problem in our buildings. Now, it won't protect the extension cord, okay? Yeah, I mean, unless the cord is nice and thick. And we use lots of cords that are well below the capacity of the circuit breaker. So you have to be careful what you plug into the extension cords. Well, thank you for watching. And like I said, in the next session or two, we're going to be dealing with how we deal with the voltage drop, which can affect our device and even damage it. And then we'll eventually get into transmitting electricity long distances using devices that use the same principle as the Jacob's ladder and the ring shooter. So I'll see you later. Thanks for coming.